Hello, everyone, and welcome to another wonderful day of Pecan. So, last time we were building up this idea that of irreducible representations, and that these irreducible representations can either be one or two-dimensional. But I kind of left off with this odd question of what does a two-dimensional representation, irreducible representation, really look like? So we're going to kind of start today by looking at an example case of a 2D irreducible representation. And that's pretty much going to be playing around with C3V symmetry. So specifically, I like looking at this as the px and the py orbitals of ammonia. So these are going to be the orbitals that are going to point uh, in kind of the plane of the molecule, with that traditional lone pair pointing out of the board being the pz. So looking at these two cases, it turns out that these two will form a two-dimensional irreducible representation. And one of the ways to actually demonstrate this is by trying to apply our three classes of symmetry operators from C3V symmetry, which we developed last time, to these two cases. So let's go ahead and walk through our three classes. So the first of which is going to just be the identity matrix. We're going to do this very similar to how we originally were looking at symmetry operations for C2V symmetry, where I'm going to look at the interaction of x and y orbitals. So the px orbital will transform to itself, and so will the py. So we represent this with a 1 and 1 on the diagonal. This is a classic representation of an identity matrix. Now, trying to do this for the threefold rotations can get a little bit messier. So what I'm going to do is take this system and I'm going to rotate it counterclockwise 120 degrees. So just rotating kind of the orbitals. And if I rotate the orbitals, because again, these molecule centers should stay the same. So as I rotate the orbitals, what we're going to find is that this area of positive amplitude is going to now migrate into along this direction, which it turns out is going to be a little bit of a problem because I can't perfectly describe this new rotated density as either being entirely px or entirely py. It turns out the product of this rotation is going to be a linear combination of these two, which is a good first sign that we may be walking into an irreducible representation. It's going to be hard to simplify this case. And it turns out that if I rotate this density to along this bond, I'm going to be about 25% px character, but of the wrong amplitude. And I'm going to be about 75% py character, but again, of the wrong amplitude. And so what I can do is I can represent this again in a matrix notation. But because it's a linear combination, the value I'm going to plug in each of these elements are going to be my CI values, which, as a reminder, is going to be the square root of the probability of finding it in each of these cases. So again, if I rotate this density to along this axis, I'm going to be 25% negative px character, or the negative square root of 1/4. And I'm going to be 75% py character, but again, wrong amplitudes, because I'm now going to have positive amplitude along this direction, which means I'm going to be square root of 0.75 or 3/4. And again, wrong amplitude. So again, this will give me the x to y and the x to x character. But we have to do the same thing for what happens when I rotate my py orbital. So when I rotate my py orbital, now I'm going to suddenly have my density pointed out in this direction. And when that happens, it turns out I'm going to be 75% px character, but this time of a positive amplitude, and 25% of py character, but again, I switched directions, so that means I switched amplitude, so it's going to be a negative square root of 1/4 again. So this is usually a good sign that we may have an irreducible representation, as it's going to be very hard to simplify this matrix. And this is going to be compounded by what happens when I start applying my mirror planes, because don't forget, I have one last class of symmetry operations. And for convenience, the mirror plane I'm going to use as an example is the mirror plane cutting around the xz axis, so that would be down here. So if I apply the xz plane, what we're going to end up finding is that my px orbital won't move, and my py orbital is going to switch amplitudes. So this gives me a more traditional 1 for the x character and -1 for the y. Now, looking at these matrix representations, it's going to turn out that there is going to be no possible way to simplify these matrix representations, no matter how I try and make uh, these two states as linear combinations of some irreducible representation. They literally won't reduce, which gives us our name of irreducible representation. But then that gives us a new second problem. Because when I had a one-dimensional irreducible representation, I only had one number, so I could convey the entire meaning of that irreducible representation with that single number. Now, I would like to be able to use a single number that will describe this two-dimensional irreducible representation. But that's a little bit harder to do. So we need to try and find some number that can encapsulate the behavior of these more complicated irreducible representations. And the one that we're going to use is called the character, which is often represented with a chi. And all the character is I am going to take the sum of my diagonal elements. So this is going to be this main cross diagonal. I'm going to take the sum of these values, and that will hopefully represent all of the identity character, the rotational character, and the mirror plane. So when we do this, we'll find that the identity will give us a value of 2. The rotations give us a value of -1. And the mirror plane gives us a value of 0, because they end up canceling out. And what actually ends up being fairly marvelous is that if I try and apply the different element of a different operation belonging to this class, it will indeed actually give me a different matrix, both for the rotations and for the mirror plane. But no matter what you do, it always gives you the same character. So it turns out that the character of these irreducible representations can actually quite concisely convey how these orbitals or these irreducible representations interact with our various symmetry elements. So this is actually quite a powerful tool. And logically, if I try and apply this to my one-dimensional irreducible representations, it will give me the same answer as just taking the value that was present, because when I only have a single value in a matrix, my character is going to be that value. Now, one of the other things that I do want to point out, because it can become fairly significant, that if we look at the value of the identity matrix, the character of the identity matrix, this will always be equal to the dimension of our irreducible representation. So in this case, my character for the identity is 2, and lo and behold, I have a 2 by 2 or second dimensional, two-dimensional irreducible representation. And it is also worth noting that the characters of the other elements can never exceed the absolute value, or their absolute value can never exceed the dimensional character. So my C3 rotations always will have, or my n-fold rotations will always have to be in between -2 or 2 in this case, if I have a second order irreducible representation. So this is actually a nice way that just by looking at the characters of our irreducible representations, we can actually get some information about our irreducible representations back. Now, one of the other things that we would like to do is be able to convey all of the information about all of our irreducible representations into a nice, concise format. And this is where character tables come into play. So the idea of a character table is that I'm going to list the possible irreducible representations that any given point group can take, and then I'm going to list the character that each class of operations will give for that uh, irreducible representation. So one of the things that we have to watch out for is then how am I going, we've talked about how we can identify the character of an irreducible representation, but what I haven't talked about is how can I label my irreducible representations themselves. So before this, we used a more abstract gamma 1, gamma 2 notation, at which point we just give the values of 1, 2, 3, 4 into the order of which we discovered these irreducible representations. Well, that won't work if I'm trying to label an entire point group. So what we're going to do is give a letter label to each irreducible representation according to its behavior. So, for example, what dimension is it? And then if we see multiple members of an individual class show up, then we're going to give a numerical label each time that class shows up. And additionally, some point groups will have special rules, like if you have an inversion center, you may see a subscript of U or G to represent whether that individual symmetry operation follows Girard or Ungerad symmetry, as we saw way back in molecular orbitals. So we're going to be focusing in on 4 major labels that you'll be likely to encounter. So the first of which is going to actually be quite important. And this is the one-dimensional representation. So if I have a one-dimensional representation that when I apply the principal rotation, it's going to give a character of +1. So this is going to be a more symmetric form of a one-dimensional representation. These are going to be given a value of A, and it turns out that almost always the completely symmetric representation, the one that only has characters of 1, will be given the value of A1, which is we're going to see later is quite important. Now, because it turns out that there tends to be a lot of one-dimensional representations, we subdivide this class so that if I have a one-dimensional representation that has a value of -1 under a principal rotation, this is going to be given a value of B. Now, if we, as we just encountered for C3V symmetry, have a two-dimensional irreducible representation, this is going to be given a character of E. And if we have a three-dimensional, this is going to be a little bit more infrequent, but we're going to be looking for a value of T showing up in our character table. So let's take a look at what character tables actually are and why they're so useful. So when I have my C2V point group that we've been talking endlessly about, you'll find the label of C2V symmetry up in the upper left-hand corner. And then you'll have a list of the 4 classes of symmetry operations that will belong to this group. Now, one of the things that's worth noting is if you find a good character table, it's going to denote if I have, say, multiple mirror planes, which direction each of one of these mirror planes is going to be in. So, for example, our first mirror plane is in the XZ direction, and our second one is in the YZ. And this will help us keep our irreducible representation straight. So we then have 4 different irreducible representations, which we've identified before, but now we are giving them official labels. So our A1 EREP is going to be our completely symmetric irreducible representation. So this means that it pretty much behaves under all of the operators the same way the entire molecule does. It doesn't move. And so this is also this is often going to be the irreducible representation which the s orbital on the central atom will behave under. Because if I'm in the central atom, it turns out that my s orbital is generally completely symmetric. But it also turns out that we like labeling what axes coming out of that central orbital will behave under certain symmetries. So if I have a z-axis going through my center of symmetry, it's also going to have the A1 irreducible representation, which turns out to be really important because there is an orbital which entirely falls along the z-axis. And that's going to be my pz orbital. So it turns out that my pz orbital is going to have an A1 irreducible representation, as long as it's on the central atom. It also turns out that over here on the right, we'll see how combinations of our basic coordinate systems will also behave under symmetry. So if you have something that an operator that follows x squared or y squared, it's also going to be completely symmetric. But here's another important one. What about our dz squared orbital? It turns out that that is also going to be completely symmetric in this C2V point group, again, as long as it's on the central atom. Now we have a second irreducible representation that's going to be completely symmetric under rotation, but it's going to be asymmetric under the two mirror planes. Now, it turns out that there isn't actually going to be any orbital that will follow this symmetry, but if you're looking at something that depends with the radius in the z direction, that will actually belong to this point group. But it turns out that your xy, your dxy orbital will actually have A2, belong to the A2 irreducible representation. Now, the B1 is going the B1 and the B2 are both going to be anti-symmetric under rotation. But it turns out that our B1 orbital is also, B1 irreducible representation is also going to describe our px orbital and our dxz orbital. And similarly, our B2 irreducible representation is going to describe our py and our dyz d orbitals. So by looking at our character tables, this is actually really useful when I'm looking at the orbitals, at least of our central atoms, because they're already located here. And as we're going to find out towards the end of the chapter, this is also going to give us a lot of information about how various operators will behave in terms of symmetry elements. So again, it is worth noting that you are going to be provided full character tables in the back of your book, or if you happen to not have that with you, it's also present in the equation sheets that I provided you at the beginning of the semester. And again, this includes a guide as to what p and d orbitals are occupying each of our irreducible representations, even for rather larger point groups. So this is actually going to be a huge aid. Now we can examine this same process as we go to our other familiar friend, our C3V point group, which again, in this case, only has 3 classes, which means it only has 3 irreducible representations. So it turns out that this one actually doesn't have any irreducible representations that belong to the B group. Both of our one-dimensional irreducible representations transform symmetrically upon rotation, where our pz orbital is going to transform completely symmetrically under rotations and reflections. But we also do have an irreducible representation to which no p orbitals belong that will transform asymmetrically upon rotations. Now, here's where when we get to C3V point group, it gets a little bit messy because it has a 2-dimensional irreducible representation. And this is the one that we developed here at the beginning of the lecture. And as we showed, it consists of it contains the px and the py orbitals. Now, here's one of the things that becomes really important about a 2-dimensional irreducible representation. is that two-dimensional irreducible representation always contain orbitals in a paired fashion. So for example, the px and the py orbitals are going to be moving together in how they interact and behave in any molecule that has a C3b symmetry, which is actually going to have a fair number of impacts that we're going to see later, including the fact that this means that because their structures are going to be moving together, so are their energies. So our px and our py orbital in C3b symmetry are going to generate degenerate orbitals, both atomic and molecular. And now what's actually quite cool is this also applies to the dx squared minus y squared is going to form a paired set with the dxy, and the dxz and dyz are also going to form a paired set which will interact together. And this is actually a very cool phenomenon. Now, again, one of the things I do want to emphasize is every single point group is going to contain at least one irreducible representation that is completely symmetric. I've said this before, and I do want to really emphasize it because this is one of the most important irreducible representations. Due to the nature that it's going to be completely symmetric, this tends to be labeled as A1, except for under a very few special circumstances. So if you see an A1 point group, this is going to represent our completely symmetric representation. And this is going to be a fairly important feature. First of all, because it always represents s orbitals on the central atom. And second, because it's going to be show up quite significantly when we try and take integrals of systems, which we'll be working with next time. And one of the reasons why it's going to show up is because now we figured out what irreducible representation every single one of my orbitals lands in. So if I know an orbital, I can quickly find out what irreducible representation it belongs to if it's on the central atom. And I'll usually actually have to apply my operators to determine its irreducible representation if I'm working on a more molecular scale, and my orbitals are not centered on the central atom. But here's going to be the real question. Once I know that, how can I put this to use and why does it matter? So what we're going to be doing is next time we're going to be focusing a little bit more on how I can use symmetry and these irreducible representations to provide some information about how atomic and molecular orbitals will interact. Until then, take care and stay healthy.